Hello there, we're going to look today at exercise 4D. Now we're going to look at a couple of things actually. It's the modulus and the argument of a complex number, and also a new way of finding angles as well, which you possibly haven't seen before. So first of all, the modulus of a complex number is generally thought of as just being like the length of the line that you get from the origin to the end of the complex number. So here I've written 3 plus 2i. You can see it goes 3 across, it goes 2 up. It's a right angled triangle, and really I'm just trying to find the length of that line, so it's not really surprising we're going to use Pythagoras. It's going to be 3 squared plus 2 squared, then square root the answer. Now this is generally written with an r like this. And so I've written the modulus of z is r, which is the square root of 3 squared plus 2 squared, and that's root 13. Notice there's an alternative way of writing this. You can write this as mod z like this, with the two lines either side of the z. So the modulus of z is root 13, and obviously that's well, 3 point something. I don't know exactly what it is. You tend not to actually work it out, so I'm typing it in now, root 13, and it's 3.61. But really, most times you just write it as root 13. It's a better answer. So I want you to find the modulus of these. You know, in each case, you're going to write 3. The first one says 3 plus 5i, so you're going to go, draw a little sketch. You might find a little sketch helps. It goes 3 across, it goes 5 up. I just want you to find that. Obviously negative ones don't really matter, the fact it's negative, the length is the same. It's minus 2, so that's 2 left and 1 up plus I. But you'll still use 2 and 1 to find the length of r. So find those for me, and I've just, question 2, I've just written it using this alternative notation. The same trick applies. Just putting the hats on those square roots. I want you to find them. So pause the video. Do all, 10 questions, and then I'll put up the answers. So look, there you go. I'm hoping you've done those now. Here's the answers. Hopefully you've got them right. If you haven't, quickly do them now. But here's what my answers were. So you can hopefully look at those and go, yeah, that's what I got. And notice again, every single time I got a square root of a number I couldn't write properly, you know, I wrote it as the third. I didn't write the decimal. So that's what we do with in terms of finding the modulus. We also need to find the angle, and the angle is given the name of argument. But unfortunately the argument is rarely written in degrees. They're usually written in radians. Now I need to show you what a radian is. We actually come up to this properly in year 13, where we do this for normal maths, but you need it now, so that's why it's on this here. And this is the logic. We define 1 radian to be the angle that you'd get if you was to draw a sector of a circle which has the same radius as it has the length of its arc. Now you just need to think about that. Now normally a circle, of course, all the way round has a circumference, and you might have been taught it as pi times the diameter. An alternative to that is 2 pi r. Because obviously the diameter is twice the radius. And what that means is we've effectively, if I say to you, hang on a bit, I'm only looking at that part of the circle where that is r, I've got a fraction of the circle. In fact, the fraction I've got is r out of the 2 pi r. That means I've got 1 out of 2 pi. That's not very nice, but that's, yeah, you can think of 2 pi is about 6, so it's roughly a sixth of the entire circle. If I was to draw the entire circle, it would be roughly equal to a sixth in terms of the length of the arc that I've got. Now bear in mind, I know 360 degrees is all the way round. So if it was exactly 6, I'd say it was 60 degrees. But here it's 360 divided by 2 pi, because I've got a 2 pith off the circle. And if you type that in, what do I get when I type it in? So I get 360 divided by this 2 pi, and I get 57.29. In fact it's 57.29578 or at some point degrees. And of course I don't really need any of that. I just need to know it's roughly 57 degrees. This roughly 57 degrees if you want to do this. And from now on then we can effectively, this was my posh way of doing it, in a completely different way actually, but it's the same logic. And notice I've used 2 pi r, I've used my fraction of my, I've done it as a fraction of 360. I've used, rather than using r and 2 pi r, I've used theta out of 360. And if you do it that way, you get 57.3 again. So the same method, just different. Now, one consequence of this is it basically tells me that pi radians is 180 degrees. Now, this is worth learning. Write that down. Because on the basis that pi radians is 180, there's lots of other things that we need to know as well. So write that down, really important. And I did say to you there's other things, and these are going to be it. So from now on, think of this as 0 degrees here. There it is. Now I'm saying this is where we're going to start measuring angles from. If it's got no angle at all, we're going to say the argument is 0. But as you go round, notice 45 degree line here is now, you can think of it as a quarter pi, because 4 45s would be 180, so it's like a quarter of 180. So you just go round as you go round this way. This is half pi, or if you prefer 90 degrees, but we need to be able to do it in radians as well. So it's weird that I'm now going to be writing angles in terms of fractions of pi. It's worth you writing down that half pi equals 90, a quarter pi is 45. This one here will be 3/4 pi. That's equivalent to 135 degrees. And if you went the other way around, of course we went this way around, we went in the anti-clockwise direction. If you go in the clockwise direction instead, you have to call them negative angles. So this is minus a quarter pi, and that's minus 45 degrees. Or minus a half pi is minus 90. Minus 3/4 pi is minus 135. And if you go all the way, you actually get to 180 degrees, which is, as I've said, is pi. Well, depending on which way around you go, it's minus pi as well. So we basically have this ability now to represent all angles on the Argand diagram. All arguments is the posh name for them, in this pi to minus pi sort of notation. Now you could go the other way around. An alternative way around is, rather than going from 0 to pi and 0 to minus pi this way, you just go all the way around until you eventually get back to where you started from. And if you do that, you get 0, you get quarter pi, half pi, 3/4 pi, pi, 5 pi by 4, 3 over 2 pi, 7 pi by 4, and then eventually up to 2 pi again, which is the same as 0. So just be aware of these two alternative notations. The argument of a complex number then. So the argument is, I showed you before how to find the modulus. The argument is this angle. That's what I was hinting at before. And when we try to find that angle, we can, I suppose last time we used Pythagoras, but remember this is just a right angle triangle. This might make you think, oh, a bit SOHCAHTOA. And SOHCAHTOA effectively is what we're going to use to find it. And you'll notice the 2 is opposite the angle I want. So that's opposite. And I've got this 3, which is the adjacent. That was the opposite, wasn't it? So I can tick the A's, and you can see I've got 2 for the tangent. So and it's always the tangent I'm going to use. So we use SOHCAHTOA, and it's, as I said, this is called the argument. That's a strange word for an angle, isn't it? So you might want to just write down the angle is called the argument, and usually written argz. So the argument argz, which is, I've called theta here as well, is the inverse tan, because it's tangent here, it's inverse tan of the opposite over the hypotenuse, inverse tan of 2/3. And if you type that into your calculator, according to me, when I just did it, I've got 0.588 radians. Now, in terms of angles, what is that in degrees? If you, that's about 33-ish, 34-ish. So you can, sometimes they let you off in the exams do it in degrees, but very often they want radians. So that's why I've done it in radians. You're going to have to get good at radians. And I've highlighted it there. This argument is usually written in radians. So get used to the fact that you're expected to do these in these new angles. The 4 quadrants, I should point this out to you because it's not quite as easy as you would think this. Because the arguments can go, first of all, in 2 different ways. So depending on whether or not you are measuring this in the 0 to 2 pi direction, or the possibly the minus pi to pi direction, it determines which one answer you give. So say this angle up here was, I don't know, arg, I've got an arg, I'll write it here, arg z equals, I'll just say it's 1.2 radians. Okay, now it doesn't matter which method you'd use here, it would both be equals 1.2 equals 1.2. If I get an answer in this quadrant here, it doesn't matter how I write it, because effectively both methods are the same in this quadrant. So whether I'm labeling it from minus pi to pi or from 0 to pi, 2 pi, it makes no difference. And it actually, that's nice. But notice over here, when I find using SOHCAHTOA my angle, that will be my angle. That's what I will get when I find SOHCAHTOA and get my angle. That's why I've called it theta. But the argument is here. This is my argument. That's arg z. So notice how I've got to really do 180 degrees, take away the angle. But we're not using 180 degrees. So that's why, because I know 180 degrees is pi radians, I now have this notation instead, or this calculation to do. And again, it doesn't really matter which one it's in, because in both quadrants, in that quadrant, both methods give the same answer. It doesn't matter if it's 0 to 2 pi or minus pi to pi. Effectively, it only matters when you're down at the bottom. And SOHCAHTOA, and now we're down at the bottom. So if I measure this angle, I might get this angle here to be, I don't know, arg z is, I might get that theta equal to 0.8 radians. Notice how it's not really 0.8 radians, because the argument is minus theta. So therefore it's minus 0.8. Or alternatively, if I'm measuring that way round, I would normally do 360 degrees minus my angle. But again, 2 pi is really 360, so it gets complicated. And then I've got this final one. Now, if I go this way round, notice again, when I do my trigonometry, I will find this angle here, not all the way around there. So I have to add on, potentially, if I'm doing this 0 to 2 pi method, I have to add on 180 degrees, or pi. But if I'm going this way round, I have to do 180 minus that angle. And it's actually is then even then wrong, because really it's theta minus 180, because I've got to get the answer to be negative. And notice again, you switch that to a pi. Now here's an example of it. I've got the answers there, so that will help us. Find the argument of this complex number. It says minus 7 minus 4i. So if I draw it, minus 7 is over there, and minus 4i is down. So there, something like that. That's the angle I want. Okay, now I can find that easy enough. It's the inverse tan of the opposite, which is the 4, and the 7 across. So if I do that, the inverse tan of 4/7, I get 0.519. And notice that's not actually the answers here I've got. Okay, and that's because that's just this angle here. But we measure arguments from this line here. So I have got to find this angle all the way to that line. And the way I do that is I add pi on. Pi is equivalent, remember, to 180 degrees. So if I do that, I'll add pi on, I get 3.66, which of course is the answer they've given me. But an alternative is to do this method, and to do that I do theta minus pi. So if I do that, what was it? It was 0.519 minus pi, and that gives me minus 0.262, which is this one. So look, here's a few questions for you to do. This is what I want you to play with. You can do that at home. Pause the video now. Look, I'm hoping you got those right. I suppose you'll only know once I show you the answers. So here are my answers. If you haven't got them right, go back and see if you can get the right answers. In class we'll do exercise 4D. It's mainly worrying about degrees and radians.